they'll just join in on wherever we are. But welcome to class 3 of Intro to Geometry. My name is Izzy, and I believe Adrian, my TA, he'll be here later. He will be late. So as I mentioned last week, I can't really look at this chat while I'm presenting because I'm screen sharing. So, but because Adrian isn't here, I think I will try to like toggle back and forth a bit from the presentation and checking the chat. Oh, okay. So,
Excuse me.
yes.
I have a suggestion.
Yes.
You could choose one of us to sort of read through the chat, so we could just tell one of us could just tell you if something's in the chat.
That's true. I think Cloud Classroom just sent a chat and they said that they can cover the chat questions for today until Adrian comes. So I think we'll do that. But thank you for the suggestion. Next time, if we want to do that, we can also do that too. Okay. Yeah. So today, like I said earlier, I think we didn't finish. I would say like one problem from one section from chapter 2. So I would like to go ahead and get started on that, and then we will jump into chapter 3, which is about congruent triangles. Okay, so let me screen share.
I know something about triangles.
You do?
Their three angles always add up to 180 degrees.
Mm-hmm. That's correct. Okay. All right. Okay. It was this one. Okay. So I'm pretty sure that's all right. Okay. Yeah. Okay. So section 2.7. This is where we left off from last class. But section 2.7 is about parallel lines, and we're going to revisit the concept again. And we are also going to learn about basically converse statements. But basically, a converse statement is something it's basically the backwards version of the original statement. For example, if we have a true statement of the form, if this then that, then the converse, which is going to be the backwards, it's going to be if that then this. So even if our original statement, if this then that is true, that doesn't necessarily mean that the converse, which would be if that then this, is true. Okay. So then we have to prove the converse separately. And basically what we would have originally done, I would say last class, was I actually did not include the problem. I think I skipped over it because it was more of a straightforward problem. But basically what the problem was, it was showing was how it was giving us a statement, and then we proved how that statement, the converse of that statement, was false. But it was pretty straightforward problem, so I just skipped over it. But yeah, that was what the focus of the problem was. Okay, so now we're going to work on this problem though. But yes, so I actually figured out a way to be able to include an image of whatever problem that we were working on the whiteboard software or program thing online. However, I didn't like use the method for this problem yet. I started figuring out that you could use that method for chapter 5 problems, after I started working on chapter 5 presentations, but for chapter 3 and 4, they're not really going to be necessary because I'm going to be staying on chapter 3 slides for the most part, I think, except for one problem. And then chapter 4 is very short, I would say, compared to like chapter 2. It's on the shorter side, so I didn't really seem it necessary for me to have to go through the entire method because it is a bit lengthy. But yeah, I just wanted to give you all a heads up and just let you know that I have come up with a solution. Okay, so problem 2.25. Given that the triangles are as marked in the diagram, prove that line segment AB is parallel to line segment CD and line segment BC is parallel to line segment AD. Okay, so go to the whiteboard software, and then I will draw the image. Ooh. Also, we don't have to deal with my not too great drawing skills on a drawing pad. Okay, and this is 80 degrees, 30, 70, 80, and so basically we want to prove that segment AB is parallel to segment CD and that segment BC is parallel to segment AD. Okay, so let's first tackle this problem by figuring out all the angles in the two triangles. So as we figured out last week, basically, if you add up, and as Max previously said, if you add up all three angles in a triangle, you get 180 degrees. So let's do that for these two angles. So ACD is going to be equal to 180 minus 30 minus 80, and that is going to be 70 degrees. And then at the same time, if we do the same for angle ACB, that means that we would do 180 minus 70 minus 80, which is going to be 30 degrees. So once we have gotten that down, we can figure out that angle DAC is equal to angle ACB. So angle DAC is equal to ACB, meaning that segment AD is parallel to segment BC, AD and BC. And at the same time, because angle BAC is parallel to, or it's not, it's the same as the angle DCA, AB is going to be parallel to CD. So I think that was pretty straightforward. All right. And then I will check the chats now. Oh wait, no, reading up bring the chat or Cloud Classroom. Okay. All right. So that was chapter 2. That was just the one problem that we did not do. I thought that was pretty straightforward. And at that point, I would like to move on to chapter 3. All right. Okay. So chapter 3 is about congruent triangles, as I previously said. This is a longer chapter, so my original schedule was to when I guess 10 minutes have approximately passed. So I guess we could say at 7:45 we can have a break up until maybe 7:50 or 55, depending on how long of a break we want. And then for the rest of the time, we can use that time to learn more about congruent triangles. Okay. So 3.1 is an introduction to congruency. So basically, two figures are congruent if they are exactly the same. So if you look at figure 3.2, you can see that all the markings show us all the sides and all of the angles of the two triangles are the exact same, therefore they are congruent. And we use this symbol right here to show that two figures are congruent. So example, triangle DEF is congruent to triangle QPR. Okay, note, we are careful to put the vertices in the same order, and we would not write triangle DEF is congruent to triangle PQR. So we want to make sure that we would start at the same vertices, so then the correct notation would be DEF to QPR. And yeah, oops, okay. And if we have two congruent triangles, all the corresponding pairs of sides as well as the corresponding angles are equal, as seen with the markings. Okay, so next we have section 3.2, SSS congruence. So SSS stands for side, 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 and then congruence theorem. Basically, this theorem states that if the lengths of the sides of one triangle equal the lengths of the corresponding sides of another triangle, then the triangles are congruent. So an example of this would be triangle ABC being congruent to triangle XCY by side, side, side congruence. So let's take a look at the example. You can see that because of the markings tell us that they have three congruent sides, that means that these triangles are congruent. And the concept is that we want to recognize two seemingly different situations, recognizing two seemingly different situations as the same can be a powerful simplifying tool in math problems. And in geometry, this often involves recognizing symmetry, and this is incredibly important. This is a very big concept, I would say, in geometry. Okay, next we have problem 3.3. So as I said previously, I'm not going to be using the whiteboard feature as much today because these problems are going to be dealing with, I would say, proving or showing that the triangles are congruent by different theorems. And I guess it's more like word related or concept related rather than math, trying to actually work out problems related. So yeah, so because of that, I will be staying on the presentation more than actually going back and forth with the whiteboard software. Okay, so next we have problem 3.3. In the figure, the sides and angles have measures as shown, and we want to find angle LN. So I will display the words up here. If you want to read ahead, you can, but I will conceptually explain the problem so that if you don't understand it, then you will be able to understand it. Basically, we can see that segments LO and MN are congruent, or they are equal to each other, and then sides LM and ON are also congruent, and that's because they have the same measurement. So we got two sides down, and then if we look at LN, LN is going to be congruent to itself because it's LN is equal to LN. So then we can use SSS congruence theorem to prove that these two triangles are congruent to each other, which means that the angles are also congruent to each other, Therefore, we can see that angle LNO is 25 degrees, meaning that angle MLN is going to be 25 degrees. And here's a note below. Once we determine that two triangles are congruent, we can apply whatever we know about the sides and angles of one triangle to the other triangle. So this is what we just did by figuring out that these two triangles are congruent by SSS. So we knew that the sides were congruent, therefore we also knew that the angles were congruent. Okay, so this is a concept related to radius and chord. Important. If a radius of a circle bisects a chord of the circle, so here's the radius, and then here's the chord, bisects a chord of the circle that is not a diameter, so we can see that this is not the diameter, then the radius must be perpendicular to the chord, and that can be shown, or that can be seen with the 90-degree angle marking. And it also works in reverse. A radius perpendicular to a chord must bisect the chord. Okay, next we have exercise 3.2.3. So in the diagram at the right, AB is equal to 7, AD is equal to 4, CD is equal to 4, and BC is equal to 7. Prove that angle ABC is congruent or is equal to angle CBD. Okay, so let's just, I could go on the whiteboard software for this one, but I think it's not too hard to imagine. But let's imagine that we drew a straight line from D and B, so then we would get segment BD, and this shape would eventually have two triangles. So we know that AD is equal to 4, and we also know that CD is equal to 4, which means that these sides are going to be the same measurement. We also know that AB is equal to 7 and BC is equal to 7, so these two sides are going to be the same measurement. And then BD, if we were to just imagine that BD is there, we know that BD is equal to itself. Therefore, we can prove that these two triangles that we formed by drawing BD they're going to be congruent to each other. So then, if we know that they're congruent, then we can say that angle ABC is congruent. Oh, I meant to write ABD. Sorry about that. Angle ABD. We're trying to prove that angle ABD is congruent to CBD. My apologies, not ABC to CBD. But so the main concept of this problem was to show that once we know that two triangles are congruent, we can basically say that the sides and the angles, specifically angle ABD and angle CBD, are congruent. I did that because I did not realize I made a typo there. My apologies for that. And I made the same typo down there. Okay. So next we are going to 3.3, which is we're going to be learning about SAS congruence. So SAS stands for side angle side, and that's the name of the theorem. If two sides of one triangle and the angle between them are equal to the corresponding sides and angle of another triangle, then the two triangles are congruent. I don't have an image for it, but we are going to be using a problem to show an example of using SAS, and that will, I think that will make the wording, or it'll make the theorem easier to understand. Okay, so next we have problem 3.7. So point E is the midpoint of both line segments AC and BD. Prove that line segment AB is parallel to line segment CD. So I am going to be displaying the words. So we know that AE is going to be equal to EC, and we know that so BE is going to be equal to ED. And we also know that angle AEB is going to be equal to angle CED because they are going to be vertical angles. And because we know those three pieces of information, we can conclude that a triangle ABE is congruent to triangle, AEB is congruent to triangle CED by SAS. So because we know that, we can prove, or we can figure out that angle ABE is equal to angle CDE, therefore angle, and then also angle ABD, this bigger angle I would say, or it's the same as ABE, but ABD is equal to CDB, and that proves that line segment AB is parallel to line segment CD. Okay, next we have problem 3.8. So in the figure, AD, there should be no comma there, AD is equal to CD, and AB is equal to BC. And we want to prove that the line segment, I realize that it does not specify. I have a typo. I meant to say, let's see, prove that line segment is perpendicular. I meant to say DB. Line segment. I did not realize that I have quite a few typos. I'm sorry. I apologize for that. It's perpendicular. Okay. So yeah, basically our goal is to prove that line segment DB is perpendicular to line segment AC. All right, now I'll display the words again. So we want to prove that the two lines are perpendicular, but we lack information about the angles. So we look at the 4 different triangles because that's going to give us information about the angles. And given these side equalities and seeing that BD is equal to BD, that's going to give us DAB is congruent to DCB because we see that DC is equal to AD, CB is equal to AB, and then DB is equal to DB itself. So that's going to give us triangle DAB is congruent to triangle DCB by SSS. However, this does not give us information about point E, or the angles at point E, but we can figure out that angle ADE is equal to angle CDE. So then together, with AD being equal to DC and DE equaling DE, this gives us triangle ADE is congruent to triangle CDE by SAS. And because of that, we can declare that angle AED is congruent to angle CED. And since the two angles are also supplementary, we have angle, so that just, we have angle AED is equal to 90 degrees and angle CED is equal to 90 degrees. Therefore, BD is perpendicular to AC. All right, so next we have 3.4. This is going to deal with 2 new theorems. So the first theorem is the angle side angle congruence theorem, which basically states if 2 angles of one triangle and the side between them are equal to the corresponding angles inside of another triangle, then the 2 triangles are congruent. For example, in the diagram below, we have triangle ABC is congruent to triangle DFE. So we can see that we have angle E and C are equal to each other, angle D and A are equal to each other, and then side DE is equal to side AC. So it's basically angle, side, and then angle, hence the name ASA. Next, we have angle, angle, side, congruence theorem, and this one states that if two angles in a side of one triangle can equal the corresponding angles inside another triangle as shown below, then the triangles are congruent. And we have to be careful when we're using this theorem because the equal sides must be adjacent to corresponding equal angles. So if we look at the example directly shown below, we can see that they are not congruent angles because the equal sides are not adjacent to corresponding equal angles. So if we wanted it to be congruent, BD would have to, or that's not BD, BC would have to be equal to EF. Or no, yes, sorry, yes, I was originally correct, yes. BC has to be equal to EF for the theorem to be able to be applied to the triangles. But on the right, here's a correct image of AAS being used. So we can see that we have angle C is congruent to angle F, angle A is congruent to angle D, and then we have side AB is equal to side DE. Therefore, the two triangles are congruent. Okay, next we have problem 3.12. So in the diagram, AD is equal to BC, AD is parallel to BC, and E and F are on AC, so that angle ADE is equal to angle CBF. And we want to prove that segment AB is parallel to segment CD, and that DF is equal to EB. Okay, so I will display the words for this one again. Okay, so because we know that AD is equal to BC, that angle DAC is equal to angle BCA. Is that correct? Yes, because the line segment DAC is equal to, it should say, sorry, CBA. I cannot, the amount of typos that I have today. I'm sorry. This is embarrassing. I don't know why I have so many typos, but that should say CBA. Okay. And we are back to presenting. Oh, wait. No. DAC, was I originally correct? I was originally correct. Oh my gosh. Okay. I was looking at angle ADC and CBA. That just tripped me up a bit. So it was originally C. Right. All right. Let me just. No. Go back. Whoops. I went way far back. Okay. BCA, DAC. Okay, that was what I was originally trying to say. Okay, I apologize for that. Okay, but okay, so since we know that AD is equal to BC, angle DAC is equal to angle BCA because segments AD and CB are parallel to each other, and AC is equal to AC. We can say that triangle CAD is congruent to triangle ACB by SAS. And therefore, this means, Siri, sorry. Therefore, angle DCA is equal to angle BAC. So line segment AB is going to be parallel to line segment CD. And additionally, we can figure out that angle or triangle DAE is going to be congruent to triangle BCF by angle side angle. And if we look at triangles ADF and CBE, we can see that we already have a congruent side and a congruent angle, as seen with angle CBF and EDA, and then AD being equal to BC. And then also we can figure out that AF is equal to AE plus EF, which is also equal to CF plus EF. And therefore that means that AF is going to be equal to CE, and that gives us a second side. So triangle ADF is going to be congruent to triangle CBE by side angle side. And on top of that, we can finally conclude that DF is equal to BE. And here's a side note. In complicated geometry problems, we can, I would recommend marking the side and angle equalities as you find them so that your life gets a little bit easier and you don't have to kind of like retrace your steps, but or retrace your logic, but instead you can see that, oh, okay, these sides and these angles are congruent, so then these triangles are congruent, and et cetera, et cetera. So yeah, as you work out the problem, make sure that you are marking the angles and sides that are congruent, and your life will get easier and you will be able to get to the solution easier too. Okay, next we have 3.5, which deals with SSA and how it is not necessarily, it does not mean that the triangles are congruent. So SSA, which stands for side-side angle, is not a valid congruence theorem, and you cannot use it to prove that two triangles are congruent. So, and we're going to see why we can't use SSA with this next problem. Okay, so problem 3.14. Figure out why there's no side-side angle congruence theorem by building a triangle with AB equaling 1.8 centimeters, BC equaling 1.5 centimeters, and angle BAC equaling 40 degrees. So I cannot necessarily, I guess I could show that I'm using a rule and everything, but to make life easier and to keep moving on with the lesson, I am just going to show you an image that would result if we were to actually draw out AB, BC, and then angle BAC. But basically, so we're going to first draw AB, so this would be 1.8, and then we would draw BC, which is 1.5, and we know that because BC is shorter than AB, then that means that it cannot be the longest side. In case you guys were thinking that BC might, and it might end up being, this is called a hypotenuse. We're going to learn more about triangles in the future, but in case you thought that it was going to be the hypotenuse, it can't because it's shorter than AB. And then angle BAC. So this angle right here is 40 degrees. So let's just say that we actually did draw that, and they included, or the solution includes it on a circle, because I think it just makes life a whole lot easier if you were to include the triangle in a circle. I believe that you could perhaps solve this problem without drawing a circle, but because the circle's there, the problem is I would say it's much easier to figure out. Okay, so let's say that we drew it, and we start as we have before, drawing AB with like 1.8 centimeters. Since BC is equal to 1.5, this must mean that C must be in a circle. So you can see that there are two C's because we will figure out why later, soon. C must be on a center with center B, and this would end up being the radius. So BC would be the radius. And also because BIC is a 40-degree angle, C must be on a ray from A. That makes a 40-degree angle with AB. So this is the ray right here. And here is the ray in the circle. So it looks like the ray hits the circle at 2 points. This is why we have C1 and C2. And if we go back to the original information, we can see that both triangles created, so triangle ABC 1 and ABC 2, match the information we are given about triangle ABC, but we can see that they're not congruent. So this means that we cannot use side angle to prove that triangles are congruent. Okay, next we are going to learn more about isosceles and equilateral triangles. These are, I think, two of my favorites.
I know something about equilateral triangles.
You do?
All the three sides are equal.
We'll learn more about equilateral, I think, on the next slide.
And there's another type of triangle where every side is different. Isosceles is only two sides that are equal and one side isn't equal. And isosceles the triangles can at least have two acute angles. Should at least have two acute angles. Or three.
Yep.
You should have two or three.
So, as Max said, an isosceles triangle is a triangle in which two sides are equal to each other, and the equal sides are sometimes called the legs of the triangle, and the other side is called the base. So, if we refer to the image, we can see that this is an example of a triangle ACB is an example of an isosceles triangle because we can see that the legs of the triangle are congruent to each other, and then this is going to be the base. But we can see if two sides of a triangle are equal, then the angles opposite those sides are equal. So these equal angles are often called the base angles of the triangle. So, and the other angle, the vertex angle. So the base angles are going to be, they will be touching the base, and then the other angle is going to be the vertex angle. I think this is actually maybe a better image of an isosceles. This is how I usually imagine what isosceles triangles look like when I think about them. But here's an important memo about isosceles triangles. So if AB is equal to AC in triangle ABC, then that means that angle B is equal to angle C. So that's what we just covered. And then also if angle B is equal to angle C in triangle ABC, then AB is equal to AC. So this is just these two pieces of information is just showing us how we can identify isosceles triangles. But I think it's pretty straightforward when it comes to identifying isosceles triangles. But yes. Okay. We have what time is it? It's 7:44. Okay, we'll just go on for another minute and then we can have our, I would say, 5-minute break. Yeah. Okay. Okay, next we have problem 3.17. So we'll take a break after problem 3.17. But basically, in the diagram, AC is equal to CD, which is also equal to DB, as we can see with the tick marks. And angle B is equal to 23 degrees. And we want to find angle A. So I'm just going to describe this out loud because I think it's pretty straightforward. I don't think I have to go on the whiteboard software to um, do the math. But we can see that triangle DCB is basically, it's going to be an isosceles triangle because two sides are exactly equal. And if we know that CD and DB are equal to each other, this means that angle DBC is going to be equal to angle DCB. So then this angle will also equal 23 degrees. And if we were to do the math, we would get 180 degrees minus 2 times 23, which is going to be 46. And that would basically be equal to 134. So that means that angle CDB is equal to 134. And if we look at this next image, or sorry, next triangle right next to triangle DCB, we can see that triangle ACD is also an isosceles triangle, and which means that angles ADC and angle A they're going to be congruent to each other, and we know that angle ADC is 46 degrees. Therefore, angle A is also going to be 46 degrees. And there's the explanation that goes along with it. Okay, so I think it's a good time to take our break now. So let's see, what time is it? It is 7:46. Oh, 7:47. So let's say 7:52 would be a good time to come back. So we will now take a break. So see you guys in 5 minutes. Okay, so it's been 5 minutes, so I would like to get back into where we left off. All right, so let me share my desktop. Okay. All right. Okay. Did I muted myself. Yes. Okay. I just wanted to check. Okay. So here we go. Okay. So next we're going to learn about equilateral triangles. So an equilateral triangle, as Max described a few minutes ago, is a triangle in which all three sides and angles are equal. So we can see an example of an equilateral triangle below. So we can see that all three sides are congruent, and at the same time, all angles are equal to 60 degrees. And here's an important note. If all three angles of a triangle are equal, then so are all three sides. Conversely, if all three sides are equal, then all three angles are 60 degrees.
So that no matter how big the triangle is, the angles are always 60 degrees and all the three sides are always the same.
Yes, so as long as all angles are equal, then all sides are equal, and then as long as all sides are equal, then these three angles are always going to be 60 degrees. Okay, so now we have another problem. I believe this one is it's a longer one, I think. Yes. Oh, wait, maybe, hold on. I will be back in 10 seconds. I'm going to turn on the lights in my room. Hold on. Okay, sorry about that. All right, problem 3.2. So in the diagram, O is the center of the circle, line segment AB is parallel to line segment CD, and angle ABO is equal to 24 degrees, and angle OBC is equal to angle OCD. So we can see all of that with the markings that are in the problem. And we want to find angle BOC. So I'm just going to, I think it's just easier for this problem to have the words up. And then there's also a picture that goes along with the explanation. So basically, we have parallel lines, and then we also have an isosceles triangle, and we know that OB is actually equal to OC because they're both the radii of the same circle. So we can do some angle chasing. Angle chasing is a term that you use to basically, it refers to how people, figure out different angle measurements, and then from those angle measurements, they figure out more angle measurements, and that's why it's called angle chasing. So we let OBC equal X, so that means that because this is an isosceles triangle, OCD, oh wait, no, sorry. So OCD is also going to be equal to X, and then because it's an isosceles triangle, OCB is also going to be equal to X. And then since AB is parallel to CD, we're going to have angle ABC plus angle BCD equal 180 degrees. So then as a result, we're going to have angle ABO plus OBC, which makes up angle ABC, and then angle BCO plus angle OCD, which makes up angle BCD, those two are going to equal 180 degrees. And if we were to plug all those values in, we would eventually get the following equation, which is 24 degrees plus 3x, which will equal 180 degrees. So then x would equal 52 degrees. And then basically we would just plug it back in, or BOC would be 180 minus 2x because it's an isosceles triangle, so then that would be equal to 76 degrees. Oh, wait. Okay, so that was actually the last problem, or I did not decide to present on this because this was more, or I did not decide to present on 3.7 because it was about, it was just a review of using compass and straight edges to draw equilateral triangles, but that is hard to demonstrate, I would say, virtually. So then, and I don't think I have straight edges, and compass, mine broke, I think, or I cannot find it. It's either one or the other. But I would, if you want to learn more about how to use a compass and straight edge to draw triangles, equilateral triangles, or isosceles triangles, I'd recommend YouTube. But then again, I think unless you're maybe, I didn't actually use straight edges, and I think I rarely used compasses when I was learning geometry. I would say it's probably more common in math competitions if you're planning to, if you want to enter into math competitions. But yeah, I don't really remember using compasses or straight edges that much. So yeah, but again, if you want to learn more about drawing triangles, then you can go to YouTube. Okay, so next, we actually have quite a lot of time still. So, and I was thinking that we were going to have a lot of time. But I think it would be a good idea to then present chapter 4, which is about perimeter and area. It's actually one of my favorite sections in geometry, and I just like to figure out area in general, I would say. I like perimeter, but I like area more. But yeah, so, and this chapter is definitely on the shorter side. So without further ado, I think we can get started on this chapter. Okay, chapter 4, perimeter and area. All right, first we're going to learn about perimeter. So I bet all of you guys have come across perimeter at least one point. Definitely in pre-algebra, I would say you would learn it. I think, yes, I'm pretty sure, like 99% sure. But a perimeter of a closed figure is basically, in simplified terms, it's how far you travel if you walk along its boundary all the way around it once. For example, perimeter of a triangle, I do have a tendency, and I think a lot of people also abbreviate perimeter to PM. So that's, if you see PM, that means perimeter. But a perimeter of a triangle is the sum of the lengths of the sides of the triangle. And I think if you see an example, which is going to be our next problem, you'll see more of what perimeter is like, if you guys have not come across perimeter before. Oops. Okay, so ABC is an equilateral triangle, and we want to find AB given that the perimeter of ABC is 36 degrees. So let's go to software, which is over here. I'm trying over here. Okay, so basically our problem was asking us to, so ABC, triangle ABC is an equilateral triangle, and we want to find AB, knowing that the perimeter is equal to 36 degrees. So, okay.
I think first we need to divide 36 by 3.
Exactly. So we know that in an equilateral triangle, all the sides and angles are congruent. So then we want to divide 36 by 3 as Max said. So we are going to get 12. And and if we were to label ABC,
So
that's
AB equals.
Can I interrupt?
Yes.
Is PM perimeter?
Yes.
Oh, okay. Thank you.
Yeah, no problem. Okay, so yeah, that's actually basically our answer because there's 3 sides. Divide by 3, you get 12, and it's the side measurement of one side. So basically, AB is equal to
Only if it's equilateral, so that AB equals 12. But if it's isosceles, then it isn't going to be equal to 12.
Yep. Okay, let's see. Okay, I can refresh it later. It's fine. Okay, so the answer was 12. Okay, next we have this problem. This image is a bit harder to draw, but I can, and I didn't apply my method to chapter 4 yet, because I just came up with it and I was working on chapter 5 slides today. So I apologize for not figuring out the method sooner, but I will just pull up the words for this one because it's a bit complicated to draw. But basically, so the problem states the following. Given that each little square in the grid is a 1 times 1 square, find the perimeter of A, B, C, D, E, F, G, H, I, J. So this figure right here. So basically, perimeter is where you would add up all these sides. So that's actually really simple. And you would eventually get, I mean, that would take a longer time. And it's okay. I have the answer somewhere. Hold on. But basically, what I wanted to say was an easier way to do it is to just look at the lines that are horizontal first. So you can see, okay, BC, DE, FJ, and HI are all horizontal. And so BC covers 3, DE covers 3, FG covers 1, HI covers 1. So 3 plus 3 plus 1 plus 1, that's going to equal 8. And then AJ covers 8. So then, okay, that's 8 plus 8 is 16. And then on the other hand, if you look at the vertical lines, you can see, okay, BA covers 2, DC covers 3, and so then that's going to be 5. And then if you look at the other side, EF covers 1, GH covers 2, IJ covers 2, so then that's 5. So then that's going to be 5 plus 5 is equal to 10. So then we would have 16 plus 10, which is going to be 26. So that is, I would say that's that's more simplified way. Also saves time too. But of course, you can just go with the traditional solution by just kind of like adding up all of these sides. Okay, so next we have area 4.2. And we're going to be talking, before we talk about area, we're going to be talking about squares and rectangles. So a square is a figure that has 4 sides equal in length and 4 right angles, and a rectangle is a 4-sided figure with 4 right angles, and they have 2 sets of equal lengths of sides that are opposite of each other. I am pretty sure all of you guys have probably come across squares or rectangles at one point in your life. So yeah, we're just going over the basics. But area, I also believe that you guys have come across area too. Area is a total number of 1 times 1 squares needed to cover the figure, where we add fractional squares when we only need a piece of a square to do the job. So for example, we need 3.5 squares to cover the region ABCDEF at right. So we say the area of ABCDEF is 3.5. And we will often use brackets to denote area. ABCDEF equals 3.5. So I actually don't remember using bracket area, but I think that it is an efficient way to show that you are finding area. So I think I would try to use I would try to use as brackets as much as I can for this class. I think it also just depends on your teacher too. If they use brackets, then go with brackets. If they don't, then you don't have to use brackets. Okay, so next we have problem 4.5. So let's consider rectangle ABCD, which has AB, which is equal to CD, and that's equal to 4. BC, which is equal to 80, which is equal to 5.
I think the area is going to be 20.
Yep. Yeah.
Times 5 equals 20. So the area is equal to the width times the length.
Mm-hmm. Exactly. So yeah, basically, this is a really basic, straightforward area problem. What you do when you have rectangles is, as Max said, multiply the length times the width. So in this case, it's going to be 5 times 4, and then you get 20. So yeah, that was very straightforward. Okay, next we have problem 4.6. The length of one side of a rectangle is 4 less than 3 times an adjacent side, and the perimeter of the rectangle is 64. Find the area of the rectangle. So let us go to our whiteboard where I really want to move this. Okay, went back. Okay. So let's see. Okay, so the length of one side of a rectangle, so I'm just going to say length is equal to 4 less than 3 times an adjacent side. So let's make this length equal to x. And let's say that, okay, wait, actually here, let me do this. Let's say that the 2 sides of the rectangle are x and y. And so the first length is supposed to be 4 less than 3 times an adjacent side. So that means that basically x is going to be equal to 3y, assuming that is the adjacent side, minus 4. And we know that the perimeter is equal to 64, and we want to find the area of the rectangle. So in a rectangle, we know that the opposite sides are the same length. So that means that perimeter is going to be equal to 2x plus 2y. So then we can substitute x into this equation, and we can say that perimeter, which is equal to 2x plus 2y, is going to be equal to 2 times parentheses 3 minus 4, closing parentheses, plus 2y. So then we get 6y minus 8, and then we can add 2y, so then we get 8y minus 8, and we're going to set that equal to 64 because we know that the perimeter is 64. So if we do algebra, we can get 64 plus...
So 8,
or y, yes, y is going to equal 9. And if we know what y is, then basically we know what x is because we can plug it back into the original equation that we had with x. So then we are going to get 3 times 9, which is 27, minus 4, which is 23. So then, and the original problem was asking us to find the area. So as we figured out earlier, all we have to do with finding area of a rectangle is multiply the sides. So then we would get 23 times 9, which is equal to 207. So that will be our final answer. And I forgot to mention about this, but when it comes to units for area, you want to make sure that you square your units. We don't have units in this problem, so then if there are no units, what I usually do is just say that the area is equal to 207 units squared, because we don't know what the units are, so then we just say, okay, that's what you would use for the units part. But yeah. Okay, so we can go back to our presentation. And next we're going to learn about the area of a triangle. So to find the area of a triangle, we select one side to be the base and the perpendicular segment from the vertex opposite of the base to the, or opposite to the, I think I meant to type just to the base, not the base, extended if necessary, is the height. This is a bunch of words, but I think we all know what the area of a triangle is, or we have at least maybe come across it. If you haven't, then the formula is base times height divided by 2, or I personally like to go with 1/2 times parentheses base times height better. But it's honestly up to you. It's your preference. And also, height can be referred to as altitude too. Just want to make a side note on that. Okay, so next we have problem 4.8. And in problem 4.8, we want to find the area of triangle DEF, given that J is on line segment EF, DJ is equal to 8, and line segment DJ is perpendicular to line segment EF, and EF is equal to 7. So we can basically just use the knowledge that we just, or figure out the area by going with what we just learned. So I don't know if I have to go to my whiteboard because this is pretty, it's like a plug-in equation problem. But basically, if we know what the height is, so, and then we also know what the base is, which is 7, and we know what the formula for area of a triangle is, which is 1/2 times base times height. We just plug in the numbers, so then we get 1/2 times, here, I'll just, there we go. 1/2 times, or 7 times 8 divided by 2, and then our answer would be 28. So that was pretty straightforward. Okay, next we have problem 4.9. Okay, given that angle ZXY is equal to angle XWY, which is equal to 90 degrees, XY is equal to 8, and XZ is equal to 6, and ZY is equal to 10, let us find XW. Okay, so I draw this one out. Can click here. Here we go. Start drawing. Okay. So I'm going to be referring back to this image. We have C, X, Y, and then we have that's supposed to be Y here. That looks like an X, I apologize. Right angle, and then we have 6. Oh, the right angles. Oh, there. Right angles on the wrong side, and then we have 6 and 8. I believe that's okay. X, Y, Z, W, 6, 8. Okay, and basically want to find the length of XW, and we also know that ZY is equal to 10. So I'm just going to put 10 just like that. And then W, yeah. Or here, to make it look, just to make it simpler, I'm just going to say YZ, which here, YZ is equal to 10 on the side. And we want to find XW. Okay. So this problem doesn't ask for area, and we need to find the length of XW instead. But we are going to use area to figure out what the length of XW is. So, okay, the area, let's start with what we have and to figure out the areas of different triangles. But let's start with triangle XYZ. So the area of XYZ is going to be, if we look at this, this is going to, we can imagine it this way. If you tilt your head towards the right, XZ is going to be the base, XY is going to be the height. So then we can plug that in and get 1/2 times 6 times 8. So that's going to be 1/2 times 48, which is going to be 24. Okay, so now we got that information down. So, okay, if we look, we can, let's see. Okay, so as we determined earlier, XY is the height to side YZ. So then that basically means that XYZ is going to be equal to 1/2 times, it is also going to be, oh yes, okay, it's going to be also equal to 1/2 times XW times YZ. So we're looking at the triangle in a different way, where we're saying that XW is now the height, and then YZ is now the base. So we know that XYZ is equal to 24, so we can go ahead and put that there. And we can plug in YZ because we know that YZ is equal to 10. So then we get 24 is equal to 1/2 times XW times YZ, which is 10. So then from that point, we just do algebra. So 1/2 of 10, 1/2 times 10 is going to be 5. So then we're going to have 24 is equal to 5 times XW. So then XW is going to be equal, sorry, that's supposed to be 5 at the bottom. but if we divide 5 on both sides, then our final answer would be xw is equal to 24 over 5. Okay. So that was our final answer. Okay, and next we're going to be covering same base and same altitude. So important information regarding triangles. If two triangles share an altitude, then the ratio of their areas is the ratio of the bases to which that altitude is drawn. This is particularly useful in problems in which two triangles have bases along the same line. So, and then, okay, the second point is if two triangles share a base, then the ratio of their areas is the ratio of the altitudes to that base. This might sound like, okay, so these 2 points might sound really confusing, but basically, to simplify it, there's also a problem that we will be working on. I believe it's the next slide. But basically what this is saying is, okay, so if we look at point 1, if two triangles, so if they share the height, then basically the ratio of their areas is going to be equal to the ratio of the bases. So if you think about it, there's going to be two triangles and they're going to be sharing the same height. And yeah, so then by ratio, that's like, I would say it's like a fraction. You can write it as a fraction. You can write it as like, comparing two different numbers. I'm pretty sure you guys have come across ratios in the past. They are useful in geometry, I would say. And then same thing, just imagine that two triangles are sharing a base, then their ratio is going to be the same ratio that the altitudes are to that base or the height. So that might still sound confusing, but I think you'll understand it more once we figure out this problem. Okay, so in problem 4.12, we see that segment AC and segment BC, BD, should say BD, not BC. I don't know why so many types today. I apologize. Here, I'll fix this. Okay. To presenting. Okay. BD meet at X as shown, and given that ABX is equal to BCX is equal to 15 and CDX is equal to 10, let us find the area of ADX. Okay. Let's go back and expand. Okay. So I will draw the image here. This is the last time you guys have to put up with my drawings, because this is the last problem of chapter 4. So, all right, so we have this interesting looking shape, and then we have 24x 15 10, and all the information that was said in the problem is here, so I won't rewrite it, but our goal is to find the area of ADX. Okay, so this is where we're going to apply what we just learned about ratios and like altitude and base ratios. So since triangle ABX, sorry, AB, okay, X is supposed to be right there. so that's going to make it clear. But since triangle ABX and then CDX, they share an altitude B, we're going to basically have the following, which is AX, which is AX over CX, which is that would be the base. So we are identifying the bases of the two triangles here, which is going to be equal to the ratio. So this is where we're setting up our ratio. Oops. So we have our base, and then we have our area ratio. That is going to be equal to 24 over 15. And if we simplify that, we get 8 over 5. Apologize for the background noises. Okay, so we got that information. And if we turn to triangle ADX and triangle CDX, we're going to have, we can set up a similar ratio. So we're going to get, let's see, the area of ADX, and then we're going to have the area of CDX. That is going to be equal to AX over CX. And then as you can see, we are setting up another ratio again. And similarly to the previous ratio, we can figure out that this ratio, so we have area of ADX, and then CDX, which is going to be equal to AX over CX, and we know that AX over CX is actually equal to 8/5, so that means that this ratio is going to be equal to 8/5. So as a result, if we arrange this part of the equation, oh wait, no, my bad. So let's have 5 there. So we know that, I'm just going to rewrite like a certain section of the equation, but we know that the area of ADX over area of CDX is equal to 8/5. So if we rearrange that, we are going to get ADX, the area of ADX is equal to 8/5 over the area of CDX. And from that point on, we actually know that the area of CDX is 10. So then we can just plug it in, and then we get 8 over 5 is here. I'll just write it like this to make it easier, so then I get 1 and 2. So then that means that ADX is equal to 16. Okay, so that was chapter 4, and it is now 8:30. So we are done with we are actually done with class 3. I'm going to stop sharing my screen. So yeah, today we covered chapter 3 and 4, and next class we are going to start on chapter 5. So all right. Okay. So I will see you guys next week, and thank you for coming to this session. And all right, you guys are free to go. Yes, you can leave. That's not good that you're starving. Okay.
Thank you for teaching.
Bye.